Hi, Tim.
Hey, Bob.
How you doing?
I'm doing great. How are you?
I'm doing just fine. Let me introduce this. I'm Robert Wright, publisher of the Nonzero newsletter. This is the Nonzero podcast. You're Timothy B. Lee, publisher of the Understanding AI newsletter.
That's
And we're going
right.
to talk about artificial intelligence. And we're going to start off by talking about a piece in your newsletter that got a lot of favorable attention, a lot of likes. Is this a record for likes? You were in the hundreds. You had three figures in the likes department. Is that a record for this newsletter?
Yes, I think so. Yeah, I got
Uh-huh.
200 and some. And yeah, I've got a lot of people, like 100 and 200,000 people about it read it. So
Really?
yeah, it's
Whoa,
good.
that's
Yeah.
big. That's big.
Yeah.
Congratulations.
Thank you.
And now it's our job to explain to people why this is, what the convey to them the vast illumination that is also conveyed by this piece, which they're free to go read, of course. The piece is called Large Language Models Explained with a Minimum of Math and Jargon. Now, you were on my podcast not that long ago, and we talked a little about how these things work, but it sounds like you've learned a fair amount since then. For one thing, you collaborated with a cognitive scientist. Now, you
Yeah,
have a master's in computer science, right? So you're not
that's
like
right.
a babe in the woods. But this cognitive scientist brought what kind of expertise to it? I guess cognitive science related expertise,
Yeah,
probably.
I mean, so he is a cognitive scientist who his research is kind of using part of his research is using large language models as kind of a model for the brain.
Mhm.
And I mean, because one of the things that's hard about cognitive research is you can't like take somebody's brain apart and look to see how it works. And there's many kinds of experiments that wouldn't be ethical to do. And so by looking at the ways large language models work, you can get kind of insights into maybe this is how the brain works. Obviously, it doesn't prove anything, but it's interesting and suggestive. And so
Mhm.
yeah, the way the piece came about is I was just trying to write an explainer of large language models, and I had two or three conversations with him where I just found that like he was giving me a lot of insight, and so at some point I felt I was kind of summarizing a lot of what he told me, and so yeah, I invited him uh, to kind of to become a co-author, and partly just because I wanted to make sure I wasn't like screwing anything up, and I figured if he was putting his name on it, he would be motivated to make sure that the kind of technical details were correct.
And he's got a newsletter too, right?
Yep.
Yeah. And I
Yeah,
think
it's
the
it's
piece can be
it's
found
good.
there too.
Yeah.
So and what's his name? Did you say his name?
Sean Trott,
Okay.
Trott.
Um, so now I have a little bit of a hidden agenda here. When I wrote months ago about how these large language models work, when I was just starting to try to figure it out,
Mhm.
uh, and I should add, I still haven't totally figured it out, but I ventured the idea that in a certain sense, these LLMs were kind of reverse engineering the human mind. And I haven't gotten a lot of sympathy for that view. But there's a version of it I think I want to defend. I want to keep defending. Uh, and and but before I explain why I want to keep defending it, which I'll do at some point in this conversation after we've talked about your piece a little, I want to ask you: does that sound crazy to you?
I think it depends what you mean by reverse engineering. So at the very highest level of abstraction, which I think this is something we talked about before, they're both the brain and large language models are created through this impersonal kind of bottom up process where nobody like designs it. It's you start off with this kind of random process, and then by a feedback mechanism, you try to select for a version of the brain or the language model that is more likely to achieve the objective, which in humans is obviously reproduction, and in the large language model is predicting the next word.
Yeah.
And that leads to some similar results in the sense that nobody really understands fully how the brain works because nobody designed it. It's not necessarily like it doesn't necessarily have like a clean design the way like a computer chip or something would. And by the same token, the large language model, nobody designed it. And so you can kind of poke and prod it and get a rough sense of, oh, this piece of it seems to be doing this and that piece seems to be doing that, but there's not necessarily any specific kind of overall conceptual design. And yeah, there's nobody out there that can like explain it to you because it was kind of an evolutionary process that produced it.
Yeah. I guess what I kind of mean is that by reverse engineering, I mean what the LLM has access to is our linguistic output.
Mm-hmm.
And it almost makes certain inferences about the kind of mind that would be able to produce that linguistic output. And some parts of what it does, I think, do correspond to the way our mind works. Some parts don't. But let's start off with a part that I think kind of does, which is this whole idea of word vectors.
Yes.
Now, tell me if I've got you go through this in detail, and it's fascinating. I also talked about this with Tim Nguyen, who works at DeepMind. So viewers and listeners may feel some familiarity with it. But let's take an example that's not in your piece. So, and let's take just a two-dimensional representation of a word. Now, as we'll see, these word vectors have a lot of dimensions. But if you were just going to plot a word on a horizontal and vertical axis, suppose you were thinking about animals, and the two things were kind of how potentially lethal they are and how fast they can move. Okay, so scorpions, rattlesnakes, bears would all be at roughly the same potential lethality. But in terms of how fast they move, they'd be very different, right?
Right.
And I would think that in the mind, those dimensions are in some sense represented, right? In the human mind.
Yeah.
Now, all the nobody goes in and says to the large language model, okay, I want you to map animals by lethality and by speed. But I would guess that there are dimensions of mapping that are done by the LLM that do roughly correspond to that. And I would guess that that's based on seeing sentences like, you know, I saw the scorpion and scurried away, as opposed to I saw the bear and ran as fast as I could for as long as I could. You'll have a lot of sentences with bears where people flee rapidly. With scorpions, they move away, and so on. And although these LLMs go into this with no preconceived ideas about meaning, nothing about meaning is programmed into them from the get-go, they see so many of these sentences that, given the way they are told to work in a very generic sense, they not only map words along a bunch of dimensions, they create the dimensions. They decide what the dimensions are going to be. And of course, they don't give them a name like level of lethality, but that's what they are. There's probably a dimension corresponding to that, right?
Right.
And so that's what I mean does that, you see what I mean? That the LLM is just using our linguistic output and working backwards to come up with a kind of semantic map that I think does correspond with a semantic map that is in the human mind.
Oh, absolutely. Because what it's trying to do is it's trying to predict what the next thing a human being would say. And to have a good way of predicting that, you have to model the kind of thoughts that human beings would have. Right. And so, functionally, it's absolutely trying to reverse engineer. In a semantic sense, it's trying to reverse engineer the way humans think, not necessarily in a mechanical sense, in the sense that it's like the neurons in the human brain are necessarily similar to the neurons, but yes, in a sense of meaning. And it's really fascinating. So one of the most interesting aspects of these vectors is, as I say in the pieces, you can do arithmetic with the vectors. And so if you take, if you start with a vector for man, and you start with a vector for king, and you subtract man and add woman, you get queen. And so, it's an analogy that, a queen is a female king. And there are lots and lots of examples of this. If you go from singulars to plural, from, big to bigger to biggest.
Well, here's an example from your piece. Google researchers took the vector for biggest, subtracted big, and added small, and they got smallest. So that shows that some of these dimensions of the vector, and by the way, there are like 11,000 dimensions, okay? Like I have trouble thinking of a graph that has more than 3 dimensions. There are like 11,000 something, right?
Right, yep.
And some of them clearly are about in some sense, grammar or linguistic function, as opposed to being more about meaning as we think of it. And that's a good example. Right. Another example of this math is Berlin minus Germany plus France equals, and then, that equation takes you to a place in multidimensional vector space where the closest word is Paris, right?
Yeah.
And, yeah, that seems kind of magic. I mean, the first part of what I was saying seems to me magic, or what I would say is, it is just clearly an amazingly powerful thing. You can feed all this language into it. You say nothing about the meaning, and it constructs this elaborate semantic map where words are close to other words that are similar in various respects. And I think most people are by now familiar with the results, which is that it's a whole lot like talking to a person.
Yeah. And one of the other really remarkable things is if you do this with a body of documents that includes multiple languages and doesn't necessarily have paired text, it's just a bunch of English sentences and a bunch of Spanish sentences, the large language models will get the ability to do translations kind of for free. If you just ask it, can you translate this to another language? And I think a big reason for that is it figures out that the vector space that it used for English, many of the same dimensions also will work in Spanish. And so we'll figure out, that the English word for dog is, and the Spanish word for dog should be kind of in a similar, part of vector space.
So let me get clear on this. I think originally the way translation was done was they had human done translations.
Yeah.
And they said, "Como está usted?" corresponds to "how are you?"
Right.
And they had a bunch of those things, but they showed them, they showed those correspondences to the computer. And you're saying there's a whole nother way to do translation. Now, do you feed the English in and say, this is English, and just feed the Spanish in and say, this is Spanish? No, you just feed a bunch of texts, and it kind of figures out that one is in one language and one is in another?
Yeah.
See, this is like, I'm not sure people appreciate.
I mean, this is not just hypothetical. Like Chat-GPT, you can talk to it in Spanish, you can talk to it in English, and I can't tell you there's no documents in there that have this is the English and this is the Spanish, because it's like the whole internet. But they didn't deliberately give it like anything like that. It didn't say like these are the English text and the Spanish text. It's just like a big blob of text in dozens of languages. And because what it's trying to do is it's trying to model human concepts, and concepts in Spanish have corresponding things and concepts in English. Right. And so if you figure out those correspondence, that makes you better at the prediction task, because things you learned about the world in Spanish are going to apply in English and French. And so, yeah, it's like, it's pretty magical. And I don't think we totally understand how to do that. But I think that's one of the things I find most persuasive. That's like, in some sense, like really understanding, what's happening, because, if certainly a human, if you said, here's an English sentence, what's the Spanish equivalent? And they're able to do it, you would say clearly they understand English and Spanish in some sense.
Yeah. There's another amazing example in your piece. It's drawn from that paper about sparks of artificial general intelligence. Right when Chat-GPT 4 came out, some researchers at Microsoft put this out, and they noted some striking abilities of, were they talking about GPT 3 or 4? Anyway, some striking abilities.
It was GPT 4 before it came out. Microsoft got a chance to play with it.
And these were things they called emergent because they weren't necessarily expected, I guess. But one of them was one of the ones you talk about is it's fed a bunch of texts, and some of the texts mention unicorns, and then you give it like some kind of like art generating software and say, draw a unicorn. And look, anybody who saw it would go, well, that's a comically crude version of a unicorn. Yes, but it got the basic idea. And to me, that seems a little magical.
Yeah. And important to say, so there are versions of GPT that look at images, but this was a version that only looked at words. So it had never seen a picture of a unicorn. Yeah, I assume it had read some descriptions of unicorns, and somehow had figured out, had learned to kind of reason graphically or geometrically somehow.
Because that's not predicting the next word. I mean, that's drawing something.
Right. Well, I mean, probably so the it wasn't that it was given software. It was that there was a programming language that had examples in the text of here are some things being drawn in this programming language, not necessarily unicorns, but other
Okay.
things. And
Okay.
so it learned,
Okay.
you
Ah.
know,
Okay. So it's predicting the next line of code, and it has
yes,
seen cases where
code is being used to
objects
draw
in
other
rendered
things.
in human language corresponds to certain kinds of code.
Right.
Okay. Still, I'm impressed. You know what I heard
Yeah.
recently on an AI podcast is that you know, and you'll be glad this hasn't happened yet, given how much work you spent trying to explain transformers, is that transformers aren't going to be the last word, so to speak. And they're already talking about some approach. I forget what it's called, but rather than predict the next sequence of letters or predict the next word, it's more generic than that. It just predicts the next byte. It just
Mhm.
predicts, and that means that it can handle language, it can handle music, it can handle, in principle, anything. Have you
Mhm.
heard anything about this?
Yeah, I think you're talking about there was a Meta had a paper about this. Yeah, there's a bunch of different kind of successor algorithms to transformers that people are experimenting with. I don't think it's clear if any of those are going to be important, but transformers also can be used for more than words. So like you might have heard about Google's DeepMind had a famous result a couple of years ago where they did the protein folding problem, where you're trying to predict you've got a sequence of amino acids and you're trying to predict what shape the resulting
Right.
protein will be. And this is really important for biology. And DeepMind created an AI that solved this problem that had been that humans hadn't been able to solve in a general way. And that also used a version of the transformer. So
Oh, did it?
yeah, and so yeah, it's a pretty general. So rather than predicting the next word, I'm not actually sure exactly what it's predicting, but it's predicting the next. I'm not sure the details of how that work, but they use a very
Yeah.
similar architecture. And Tesla's using for their self-driving car, they're using a version of the transformer for some of the image processing. So people are applying both the transformer and other similar algorithms to a lot of different types of problems.
Uh-huh. Okay. So, so speaking of transformers, you do get into them with some, in some depth. They emerge, I guess, from this paper in what is it, 2017, called
Yep.
"Attention Is All You Need," which came out of
Hmm.
Google
Yep.
and was, well, transformative,
Hmm.
you might say. Um,
Yep.
and so you divide kind of the magic into two steps. There's the attention step
Hmm.
where, well, why don't you go ahead and talk about, and then there's the feed forward step. Now,
Right.
first of all, is it possible to characterize, like, I mean, these are the two big steps in generating linguistic output, right?
Hmm. Yep.
And uh, how would you characterize the difference between the two steps?
So the first thing I think it's important to say is that the structure of the overall large language model is it's a bunch of transformers, and so it does these two steps over and over again. So it does an attention step, a feed forward step, and another attention step, another feed forward step. And so GPT-3, the
You
largest
mean with a
version,
given word in a sentence, it will do
yes,
those things over and over and over and over
right.
again?
And so like the biggest version of GPT-3, it does it 96 times. So it'll be 96 attention steps with a feed forward step in between each one. And so what they do is the attention step. I think about it as kind of looking around. So if for each word, it the algorithm will. So sorry, step back. And there's several. It's a little bit complicated. So there's the attention step for a given word. Um, each word is looking for other words that provide context to better understand the meaning of the word and predict what word might come after it.
Mhm.
And so in the attention step, each word will advertise the kind of characteristics it's looking for in other words. And each word will also publish, here's my own characteristics. And then it will match up the words that have the most similarities in terms of that kind of matchmaking.
Mhm.
It'll match those up and it'll transfer information from the word that had the characteristics to the word that's looking for the characteristics. So I think that an example is helpful here. So I think the example I give in the piece is if you have like a pronoun like his, and you're trying to figure out who does his refer to.
Right.
There's one that's called a query vector. That says what I'm looking for. It says maybe I'm looking for a name of a male person, and then that if say that the person it refers to is John, that word might have what's called a key vector describing its own characteristics. Say, I am a male person. And then the attention stack will notice, okay, these match, like what this word was looking for and what this word has match up. And so therefore I'm going to take information about John and move it to the vector for his, so that then the large language model understands that his probably refers to John. So that's one example, but there are each time the attention step happens, there's a bunch of different attention heads, they're called, each of which does a different thing. So one might be matching up pronouns with what they refer to. One might be doing disambiguation. So another example I use in the piece is a word like bank. You can have a financial institution bank, or you can have a river bank. And so you might have a attention head that's trying to figure out for ambiguous words, which of these. And so there.
In that case, let me ask that. So in that case, in this vast semantic space, multi-dimensional vector space, there are at least two banks. So they're in different places. One refers to like money bank, another to river bank. And what the attention step is doing in that case is just saying it's this bank. For this sentence, it's this bank. Based on what's come before, I have high confidence that it's the bank that's right here in semantic space, not the other one. But in the case of the pronoun, right, it's not like, well, you tell me, it's not like there's a version of his for every possible name, or is it in semantic space, or is it, in other words, well, you get my question kind of?
Yeah, it's hard to say. There's these 12,000 dimensional vectors that you can think. I think of it as just kind of a scratch space, right? For each word, the AI has a bunch of data that it can store about the word, and you can think about it as a vector. And some of the dimensions of the vector have the kind of thing we're talking about. But it's because they're not labeled. It's not like this is the one for size of animal and this is for whatever. It can be a little hard to tell at a very micro level, like exactly what's happening. You just observe the results. You observe. So I have an example in there where it has a sentence where there's two people, John and Mary, and they trace how it decides that Mary should be the next word rather than John. And there's like 9 attention heads that each do a little piece of that job. And if you look at it really closely, it's not, you can observe that if you disable some of those attention heads, it doesn't get the right answer. And you can tell, information is moving from here to here, but the exact kind of format or meaning of any particular bit of information is a little fuzzy. So, so to answer your question, it's going to have some information about John, whether that's literally copying kind of the name John over, or saying something like it's that word 4 steps back. I'm not. Maybe the real experts here could be able to tell you a little bit more, but it's not anything simple that you would be able to look at it and say, oh, this is anything clear. It's just adding information to the vector.
Let me ask you this: as it generates a sentence, is it so John gave Mary the, or suppose it's given that sentence, John walked into the before John walked into the restaurant, he gave his car keys to the.
Right.
And then, it's likely like valet. But anyway, as you does the attention head at any given point when it's about to generate another word, is the whole LLM predicting the next word based on some kind of aggregate summation or something that is embodied in the last word it has seen? In other words, is it just move from left to right, generating the sentence, and at any point, the last word so successfully embodies all the relevant information embedded in prior words that, in a sense, it's only looking at that word as transformed by context, you might say? That's
right. Yeah. So the attention head is looking at the previous words and plucking out whatever information it thinks is relevant and putting it in that last word. And then, so that then when you get to the end of the process, there's enough information that you can make a prediction about what the next word is going to be.
And is the mathematical operation, the key mathematical operation at that point, it's kind of located it at the place in semantic space where it just looks around for the nearest word, and that's what it puts? You know what I mean? Like,
That I don't think you can say in general. There's
okay.
at the end there's so again all of this stuff is trained through this evolutionary process, and so there's some function at the end where you take the previous word and you run it through this function and it produces a prediction for the new word. In some sense, yes, I think often there's an encoding for the next word in that last word somehow, but I don't think there's not like a real simple rule that that's definitely the vector for the next word. It's more complicated than that.
But somehow, okay, so I kind of blurred the distinction I tried to make earlier. You've got the attention step
Yes.
where it's kind of looking around at other words in order to help
grab information.
To grab information and kind of, in a sense, embed them in this one word it's looking at now, embed that information. And then you've got the feed forward step where it actually ponders the thing and generates the next word.
That's right.
Does the feed forward step always lead to, I hope this isn't the same question I just asked you. Once you're at the feed forward step and it's about to spit out the next word, is it always the case that what it's looking at is a number with 11,000 dimensions? In other words, a series of numbers and commas, I guess.
Right.
That's the output. And then it goes to that point in semantic space and snatches the nearest word?
So the final, so two things. So again, there's in the version of Chat-GPT that of GPT-3 I was writing about, there's 96 attention steps and 96 feed forward steps. So it goes back and forth between them. So it does an attention step, a feed forward step, an attention step, a feed forward step 96 times. And so each of those feed forward steps is refining the vector in a way that will make it easier to predict the next word. But then at the very, very end of the process, there's a final function that takes that final representation and produces a next word prediction. And I don't think you can say anything super in general about what that final vector is. I think often, well, so a concrete example here is, so again, remember I was saying before that I have an example where it's deciding whether to say John or Mary as the next word in a sentence involving John and Mary. There is evidence that it's finding Mary earlier in the sentence, moving it to the end. And then in some sense, there's a function that takes that final vector and spits out Mary. But it's kind of complicated, I think. But let me talk a little about the feed forward step. So the other example I have in the piece is we were talking about this, how you can use vectors to do reasoning by analogy. And so one of the pieces of research I looked at had a large language model that was answering the question, what's the capital of Poland? And this was a case where it wasn't based on the attention mechanism because the answer Warsaw was not in the sentence. And so here it had to, quote unquote, remember the fact from its training data. Presumably in its training data, there were a bunch of sentences that mentioned that Warsaw was the capital of Poland. And the way it did that is actually using this vector math. So one of the feed forward steps would take a representation for Poland and add some vector that transforms Poland into Warsaw. And then and that would produce a vector that then would predict Warsaw as the next word. I don't know if that answers your question.
Yeah, kind of. I mean, it seems kind of odd to me that it does go back and forth that way between attention and feed forward. Because every time it does the feed forward, it kind of tentatively predicts the next word, but then in some sense decides that's not good enough.
I mean, I think that's thinking about it too simply. So what the feed forward step is doing is it's also, I think, adding context to the word. So one way to think about this is to think about what the different feed forward steps do. So earlier on, it's doing more kind of low level syntactic stuff. It's figuring out, this is a noun. Adjusting, figuring out, is it so for example, in the case of Riverbank versus Financial Institution Bank,
right,
the transformer would pull in information, say there's the word river nearby, but then I think the feed forward step would then use the fact that river to kind of transform bank into the new vector. So it'd be a two-step thing. It's not that the attention step would turn the vector for bank into a river bank. It's the it would grab the information the feed-forward step needs to do
Okay.
that, and then so that's that. I mean, it's I don't know. It's hard to talk about in detail because again, we only know a certain amount.
That's the amazing thing is like kind of how little we know, and I guess I'm still a little unclear on like what I mean, obviously, large language models. Humans do create a very elaborate set of algorithms in the course of creating a large language model. I mean, they are doing, in some sense, a lot of the work, but it's still kind of amazing how much the machine does. I mean, like, here's a sentence here's a passage from your piece. How did the network decide Mary was the right word to copy? Working backwards through GPT-2's computational process, so this was an early version, the scientists found a group of 4 attention heads that they called subject inhibition heads that marked the second John vector in a way that blocked the name mover heads from copying the name John. So, I mean, this sounds like functionality, like this subject inhibition, name mover, that even the people who designed the large language models did not necessarily know would ever exist within the model, right?
Right, not at all. Yeah, that all of those steps were completely quote unquote invented through this kind of evolutionary process of training the model.
Yeah, it kind of amazes me that they could have given it instructions. I guess I would say so generic yet so powerful, embedded in the surrounding algorithm. Of course, as you suggest, the key is that it goes very much like evolution. It goes through steps of training, right? And and at this point, something called back propagation enters in. We may have talked about that. I think we alluded to this last time we talked, but do you want to talk a little about that, about what it is that makes this? I mean, just describe the whole, start from scratch, kind of describe the training. We hear the word training, but like, what does training consist of and where does this back propagation thing enter in?
Sure. So, I mean, at a very high level, all training is doing is you give the model a sentence or you give the model the first part of a sentence and you ask it to predict the next word. And when you, at the very beginning of the process, the model is trained with completely random values, and so it'll get it wrong. But then you update each of the parameters in the model to make it a little bit more likely to give the right answer the next time for the next word. And you just repeat that billions of times, and over time it gets closer and closer to the right answer. And so that's really at a high level, that's what it does. And the way it does it is that there's it's hard to really describe it without getting into the math. I mean, so there's a gradient for each the large language model is a sequence of functions where the output of one function goes into the input of the next function. And for each one, it's a continuous function, so that there's a gradient going up or it's going down. And all the back propagation algorithm does is it works backwards. It says, okay, the right answer should have been, this particular output should have been a high value and it was a low value. And so we're going to go backwards and look at, for the functions, we're going to adjust each function to make the value for that output go up. And you just go all the way back to the model and say, for every single one, how would we need to change this parameter to make the answer closer to the right answer? And the reason this is difficult is because these functions are intertwined. So they'll be, as you go backwards, a parameter will affect many different outputs. And so there's some calculus involved to figure out how much do you adjust each model to get the right output. But I don't think the details of that math is super important. It's just like evolution. Evolution takes billions of years to produce human beings. In the same way, you have to go through billions of words, and each step only makes it very, very slightly more likely to come up with the right answer. But if you do it enough, it somehow kind of figures out, the right set of weights in the model is what it's called.
And also, is backpropagation sort of a shortcut in the sense that Lamarckian evolution would be a shortcut? In other words, if they had never invented backpropagation, they could still tell these models to randomly reconfigure themselves and try again, right?
Right.
But backpropagation kind of gives them some clues as to how they might rewire themselves next time before they try again. And so, like we think of mutations as being random, and, there's ongoing discussion about in what sense they are random and so on. But, of course, what Lamarck thought was that they were highly non-random in the sense that, like, if I lift weights and get strong, my son will be born stronger, right? And there's not that much of a shortcut. The mutations are more random than that. But the point is that backpropagation kind of makes the mutations less random.
Yes, that is exactly right. Yeah. So if you imagine some sort of reproductive process where your sperm and egg could like give some kind of hint about, oh, this gene wasn't working out well, so you should pick the other gene, something like that. There's nothing like that in evolution, but yes, that's exactly what it is. It's you're sending back kind of a hint to the kind of genes of the model saying this one didn't work well, do more of this, do less of that, and that those signals flow backwards through the model so that each of those 96 layers is going to work a little bit better than it did the previous time. Yep, that's exactly right.
Let me get back to this issue of reverse engineering the human mind and elaborate a little on what I mean. I guess I'm kind of saying two things. One is we've kind of already said, which is that, the LLMs, all you give them is surface level linguistic output with no explicit instruction about meaning. And they kind of on their own construct a very elaborate, what is, for practical purposes, an elaborate semantic representation that no doubt has something in common with the semantic representation in our own minds. As you said, physically, mechanically, physical neurons are different from what's going on. But we have good reason to believe that, our brains are kind of mapping words, the meaning of words in a kind of a multidimensional space. And, what leads me to the second thing I want to say about this is there are particular properties that when you're having trouble remembering something are salient. Like we tend to remember, for example, the relative status of people. There was, when Ronald Reagan, after he had dementia, there was a case where his former Secretary of State, George Shultz, paid him a visit. And he had a pleasant conversation with him, but really didn't know who he was. And then after he left, he said to Nancy, that was a very important man, wasn't it? So he remembered the status, and the fact that was so salient is a product not just generically of semantic mapping, but of our peculiar evolutionary history. The human mind pays attention to status just as it pays attention to how dangerous animals are and how fast they run. So I guess I'm making the claim at those two levels at a minimum, and maybe that's as far as I'd go with it.
So you're saying that, because the LLMs I don't think have. I would expect they don't have a lot of that kind of baggage, in the sense that there's not.
No, but they acquire ours by virtue of processing our language.
Right. Yeah. That I agree with.
They speak as if they shared our evolutionary history, is what I mean.
That's probably true. Yeah. To the extent
they're just imitating human beings.
Yeah. To the extent it's reflected in how we write things. Yes, absolutely.
Yeah.
So I actually said something that came to mind here is that, so this is a good example actually of the kind of research you were asking what my co-author Sean Trott did. One of the things he would do is he had an experiment where he would so you have these words like bank that have multiple meanings, and there's also a set of words called what is this? Synonyms, I think it is, that are more similar. So like you could say you work at a magazine versus you pick up a magazine.
Right.
Those are very closely related words. And what he would do is he would ask people to place examples like that to rate how closely or how similar or not similar they are.
Mm-hmm.
And then he would compare that to the vectors in the large language model. As you expect, there would be a pretty strong correlation. The words that the people said were very similar to each other, the senses that people said were very similar to each other, tended to have similar vectors in a large language model. And the words that people thought were pretty different, like the two meanings of bank, those would have very different vectors. And so it's interesting because this gives, I think this is useful for linguists and cognitive scientists because it gives them a numerical way to, the large language model gives, and word vectors give people a numerical way to represent kind of fuzzy concepts like how similar are words. You can now put a number on it because you can take a large language model that generally seems to understand a language, and that then lets you do certain kinds of research that would be hard to do otherwise. So that's an example of how kind of this is useful for cognitive science.
Yeah. And just to be completely clear, the math, well, to be clear, two things. The distinction you're making between magazines is like, if you put out a magazine, to say you work at the magazine means you work for an institution that puts out a magazine. It's not quite the same as the physical magazine.
Right. The bundle of papers is not paying your paycheck or telling you what articles to write. So there's two different, there's the physical object and there's the organization. And we use the same word for it. And for the obvious reason that they're very related, the one puts out the other. But when you say he works at the magazine, our brains like automatically think, okay, that's the organization. It's not the physical thing, or it's not. I mean, there's also like a gun can have a magazine. I mean, there's many meanings of magazine, and we automatically, based on context, figure out like which meaning we have in mind.
Yeah. Now you also talk about there are two things you refer to that were in that Sparks of AGI paper that came out of Microsoft. The other one is so-called theory of mind, where we our species at least has this ability to kind of try to figure out what things look like from the point of view of somebody else. Sometimes just in a very mundane sense, like they didn't see me hide this thing in this drawer, so they don't know that the thing is in the drawer. But sometimes it has to do with your understanding of human nature more subtly. If I say this thing, they might be offended. All those things we do. And as you note, GPT has gotten better at solving the kind of mundane lab type tests. And I guess, that's another manifestation of what I'd call kind of the reverse engineering of the human mind in a sense.
Yeah.
And I would encourage, doubters on theory of mind to Google a piece I wrote for the newsletter called, I think it's like Chat-GPT has cognitive empathy or something, but it's in the Nonzero newsletter. And, I gave it this thought experiment. I said to Chat-GPT, like, suppose there's a student in a class, raises his hand, gives an answer, and the teacher says, I guess I've heard worse answers, but I can't remember when. And I said, first, how do you think the student will feel? And it got it right. I mean, it's always very circumspect. It says, well, it always starts out with this preamble. Well, it could mean a lot of things, but then it gives this list of possibilities that are in rough order of probability, And then I said, and how do you think other students in the class observing this would feel? How would they react? And it does a good job. And then I said, okay, and suppose there's a student who is romantically attracted to the girlfriend of the student who answered the question. How is that student going to feel? And it did the little preamble, but then the first answer was the word Schadenfreude. It was like, and on elaborating, it just completely nailed it. And I just, it's funny that I considered it uncanny at the time. And it's an uncanny feeling to have this conversation with this thing that keeps answering intelligently, no matter how hard you press it. But in a way, the more I think about the way these models work, in a certain sense, the less surprised I am. Is that the feeling you've had in the course of exploring the workings of these things, that it seems less and less like magic?
I mean, anything as you get more used to it, it seems less like magic. So yeah, I think that I think before large language models came along, I think it was just really hard to have a good intuition for kind of what about the human mind is like kind of complicated and difficult to explain and what's kind of simple. And so now that we just have something to compare it to, it helps us think more clearly about like what is the human brain good at, what is it not good at, and how do the pieces fit together. So yeah, I'm still quite impressed with it, and I don't feel like I really understood so the simple things, the kind of like at the level of individual senses, you can kind of trace through. This is probably why I picked this next word. I don't think anybody has a sense for like that kind of complicated stuff. I'm sure there's dozens of attention heads and feed forward networks and steps that to like come up with that answer, and I doubt anybody is close to understanding that. But at a high level, in the same way that I can understand like roughly how evolution produces wings or eyes or whatever without like actually understanding every step, I think the same kind of thing. It's like if you were gonna build an AI to like converse, it would have to have the abilities that large language models do, because to predict the next word, you need to be thinking in a human-like way because you're trying to predict what a human would say.
Yeah, I've heard people say, when you think about it, that's kind of what the human mind does. It keeps predicting the next word. I'm not yet sold on that. Does that make sense to you?
Well, I think it's not everything the human brain does. So I definitely think, like, for example, the human eye has a lot of circuitry that does a lot of pattern recognition of this, not predicting the next word. And so my guess is probably the human brain is, I don't know, pick a number, 10 or 20% a large language model, something like a large language model. And then there's other stuff. There's long range planning, and there's image recognition, and there's, so there's lots of kind of circuits that do different things. But yes, I think that there probably is, my sense is that the human mind, a lot of what we do is kind of tell stories about about ourselves and to other people. And so the idea that a lot of human cognition involves kind of, well, another thing I've really been struck by recently, I've got a 2-year-old, and how often she will pick up phrases and understand the meanings of the phrases before she understands the individual words. She'll mangle it. She's not pronouncing the individual words correctly, but the phrase she'll understand in the context. Like this is like the phrase "here you go." My wife will say that a lot, and so my 2-year-old will say "he go" and hand something to somebody.
Yeah.
And clearly she's predicting that in this certain situation, the correct set of noises to make is roughly "here you go." Long before she could like diagram that sentence and say this is the verb or this is the noun. So in some sense, yeah, I think the human brain is at a very high level a prediction machine. And language is about understanding in this kind of situation, we use these words. And over time, I think we get more and more sophisticated and at a very high level in the same way that large language models do. Although the details are obviously different.
That reminds me of something one of my daughters did when she was about 3. We were at the park, and there was other kids playing, a sandbox and shovels and stuff. And she looked at another kid's like shovel and said, "My shovel?" And I said, "No, that's not your shovel. It's similar to your shovel." And she said, "What is similar?" And I said, "Well, it means it's kind of like, but not exactly like." She said, "Oh, I call that vaguely familiar." And, she didn't know what familiar meant, and she didn't know what vaguely meant, but it was just like, yeah. But no, we are prediction machines in a lot of ways. I mean, sometimes as you go through life in terms of visual field, when you really pay attention, what you see frames your expectations about what you're going to see next. Well, I won't go into that. But anyway, so listen, we have been talking almost an hour, and it is typical or common on this podcast to do about an hour of public podcast and then go into overtime. Overtime is available to people who are paid subscribers of the Nonzero newsletter. And I'm sure that as the proprietor of the Understanding AI newsletter, you're sympathetic to all known fundraising schemes. By the way, are you keeping up your other newsletter? Your what is it? Full Stack Economics. That's on hold. Is that?
Yeah, that's on hold. So the AI newsletter has been successful enough that I'm going to keep doing it full time for at least a few more months. I mean, indefinitely. At some point, I would love to go back to writing about economics. But yeah, I'm not. It's basically on hold for now. But people should still sign up. At some point, I might. Occasionally I expect to write something, but it's not going to be my main focus.
It was courageous of you to start a whole new newsletter, because then you've got to rebuild your subscription base. Were you not tempted to just kind of change the focus of the existing one?
I did think about that. Partly I wanted to, from like an entrepreneurial perspective, I wanted to learn, like, was there a appetite for this? And so if I switched it over, I'd have a bunch of people canceling, and so I wouldn't get a clear signal. And so starting from scratch gave me a sense for how many people really wanted an AI newsletter, as opposed to like grudgingly reading the one I already had. So yeah, that's a big reason I did it. And I found it's hard. Like, it is a different audience. Like I think I've probably got maybe 10 or 20% of the people from my old newsletter do the new one. So I think a lot of people would have been irritated if I, kind of forcibly. And I think what would have ended up happening is I would have like not fully switched over. I would have still written a lot about economics and maybe not reached a new audience. So I'm glad I did it this way, because I get a kind of a clearer, cleaner information about what the market for the two types of topics are.
Okay. But enough about your newsletter. Back to my newsletter. Although everyone should subscribe to Understanding AI. So yeah, you can, to become a paid subscriber, you can go to just Google Nonzero and Substack. You can click the link in the show notes of the podcast app you're listening to. And then you go there, and there first of all, there will be a post on the newsletter corresponding to this, but moreover, if you go to the upper right, there's a thing you can click that ultimately leads you to a way to set up a podcast feed that will always have all the bonus content, all the overtimes. So in this overtime, I want to talk about. I want to get into some of the big issues that we've chewed over a little, but it's been a while since we talked. How worried should we be about the future of AI? And I saw you tweeted recently about how plausible, quote, super intelligence of the kind Nick Bosterman mentions is or isn't. So I want to talk about all that stuff. Meanwhile, thanks to everybody who's listened this far, even if you're not going to join us in overtime, but we are heading into overtime.